Well, good afternoon or good morning, everybody, depending on where you are. Athena Petropoulou and I are very glad that you are able to join us. We'll give a few seconds for everybody to transition into the break room and make sure they, are able to do that. And we're gonna go ahead and start in a little bit.
Hi, this is Reynaldo Valenzuela from Bell Labs. Am I in the right breakout room?
Yes, Reynaldo, you're in the right breakout. Yes, thank you.
That's all. I'm going back on mute.
Yes. Believe we have all of our four panelists. They have joined the room. Make sure.
I guess we're too many to see the faces. I'm not a Zoom.
Right. So we're going to go ahead and start. I know we're running a little bit late, but again, welcome. This is the 5G and Future Wireless panel. For those of you that were here also yesterday, 5G keeps being mentioned again and again, and how wireless technologies, of course, 5G and beyond 5G, are enabling a lot of the existing applications, and of course, a lot of the things that we want to happen in the future. So we have four great colleagues that have agreed to join us today to discuss anything related to 5G and beyond. And I'll ask my partner in crime, Athena, to basically go ahead and introduce the panelists. And what we've asked them to do is to give an opening statement, and then we'll have some questions for them, and then we will also open it for Q&A from everybody else. So Athena.
Very good. Hello, everybody. I'm Athena Petropoulou. I'm not chair. I used to be chair. And I wish I could see all of you, but it's nice to be among you, even if virtually. It's a pleasure for me to introduce you the first panelist, Dr. Aida Vera Lopez, who works on wireless standards. She's a research engineer at Intel Corporation. She has been focusing on 5G new radio RF topics within the 3GPP RAN4 working group. Before working in standards, she worked in various groups at Intel as part of the engineering leadership program. She has an undergraduate degree from University of Puerto Rico and a master's and PhD degree from Georgia Tech. Her research background includes millimeter wave antenna design, package integration, and material characterization at higher frequencies. For the past 5 years, Dr. Lopez served as publications co-chair of the Radio and Wireless Week conference. Dr. Lopez, I will give us a 5-minute introduction.
All right, thank you so much. Can you all hear me well?
Yes.
Yes.
Is it possible to share my screen? I have 2 slides I would like, mainly one I would like to share.
Yes, you should be able on the bottom. You see the share screen button. So
yes.
There we go. Yeah, we can see your screen. Go ahead.
Can see it? Okay. All right. So thank you for that kind introduction. Part of what I wanted to do was to kind of go over my background as it relates to 5G and future connections. So like she said, I work at Intel as a wireless standards research engineer. What that means specifically for me is that I am involved in 3GPP meetings. For those of you who are not familiar with 3GPP, they basically produce reports and specifications covering cellular network technologies. So that includes radio access, core transport network, quality of service, so the complete system specifications. Our meetings where we discuss all of these specifications include the entire ecosystem, so network operators, OEMs, chipset vendors, of course, TE vendors, so test equipments as well, and service providers. And the reason why I'm highlighting 3GPP, of course, is because 3GPP is the one defining 5GNR. So if you've heard of release 15 as being kind of the inception or the beginning of the specifications, this is a 3GPP specification. So like I mentioned, I'm part of the Radio Architecture Network 4 working group. What this means is that they're in charge of the radio performance. So defining the core performance requirements, both from the base station side and also on the UE side. And this is for both transmit and receive. And the requirement topics are kind of broken into three main categories. We have radio resource management, we have demodulation, and RF, where of course I'm focused on RF, mainly in FR2, because my background is on millimeter wave antenna design, integration, and packaging at high frequencies. I've done work mainly on 60 to 100 gigahertz, but I've gone as high as around 340 gigahertz. And I've also done some design work below that. So that's just to give a quick overview of the background and on 3GPP. But additionally, I kind of wanted to provide some context in terms of where we are in the 5G timeline from 3GPP. So we start with release 15, right, which included frequency range 1, sub 7 gigahertz, and also supported FR2, mostly on 28 gigahertz and 39 gigahertz. So those are the frequencies that were supported. In terms of the use cases, you already have the base of the enhanced mobile broadband and the ultra reliable low latency. In terms of some work items and technologies, MIMO was there from the release 15 and moving forward. This release is the first one, and then it continues to mature. So a lot of the topics and a lot of the work items that were discussed for release 15 continue to be enhanced in one way or another in release 16 and release 17. This is kind of typical in terms of maturing the technology. I do also kind of highlight here where the standalone started to come out about a year later into it, because the original one in terms of release 15 focused on non-standalone in terms of deployment, and this will impact some of the additional topics that we may discuss later today. So I kind of wanted to highlight that. In terms of release 16, some new work items include V2X, integrated access backhaul, doing unlicensed work, focusing first on FR1, and some studies on non-terrestrial networks as well. This included a study that then turned into a work item extending the spectrum to 71 gigahertz in release 17. Release 17 is where we currently are. And compared to release 15, we've already introduced higher frequency bands. So up to 48 gigahertz are now defined, and there are some requirements and ongoing discussions for different types of UEs and their power requirements at those frequency ranges. The pandemic obviously had a delay on release 17. It was supposed to be wrapped up in 2021. So there's about a 9-month delay that happened, pushing the completion to the first quarter of 2022. And then where we're headed in the near future and where the technology kind of stands, what lies ahead is really release 18. And for release 18 and onwards, this is going to be known as 5G Advanced, which you can view as kind of the in-between 5G and 6G. And we are currently discussing the scope for the release 18. So that means later this month, at the end of June, we're having a workshop to discuss potential topics to be included. And then by the end of 2021, in December, we will have a package approval, knowing which items are going to be addressed in the next release. So overall, you know, the releases have focused on developing the features to support more use cases and deployment scenarios, while still enhancing kind of the core ones that have been there from the first release. This is a typical approach as the generation matures. And with that, I think I've concluded, and I look forward to the rest of the discussion.
Okay, thank you very much, Aida. Greatly appreciate that. So it's my pleasure to introduce to everybody our next panelist, Dr. Ted Rappaport, who is the David Lee Ernst Weber Professor of Electrical Engineering at the NYU Tandon School of Engineering. He's also Professor of Computer Science at NYU's Curran Institute of Mathematical Science, and also Professor of Radiology at the NYU School of Medicine. Dr. Rappaport is the founding director of NYU Wireless, the world's first academic research center to combine engineering, computer science, and medicine. Earlier in his career, he founded two of the world's largest academic wireless research centers, the Wireless Networking and Communications Group at the University of Texas at Austin, and the Mobile Portable Radio Research Group, now known as Wireless at Virginia Tech in 1990. TED is a pioneer in radio wave propagation for cellular and personal communications, wireless communication system design, and broadband wireless communication circuits and systems at millimeter wave frequencies. So with that, Ted, the floor is yours. Please go ahead and present.
All right, thank you very much, John, and hello, everyone. Thank you for inviting me. This is very exciting to see so many names and faces of colleagues over the years. I'm going to try to share my screen, and just want to thank you, Ada Vera, for that introduction on 3GPP and how 5G is developing. I've been fortunate in my career to have a front row seat of all of the wireless generations, starting with Wi-Fi, the very first Wi-Fi as part of my PhD at Purdue, going through the first generation of cellular in the 1980s when I was at Virginia Tech, and then all the way through 5G. And what's interesting about the G in 5G is G just means generation. And so the first 4 generations of cellular, starting in the 1980s, all operated at frequencies below 6 gigahertz. So that in the wireless industry, all the companies talk about sub-6, that's below 6 gigahertz, where the first Wi-Fi standards and the first 4 generations of cellular worked. Then around 2008, 2009, the Wi-Fi industry opened up 60 gigahertz with chips for IEEE 802.11ad, an IEEE Wi-Fi standard. And like happens so often in the wireless industry, at least since I've been in it, the Wi-Fi industry is usually the first adopter and the first developer of silicon and antennas and ideas at low price points, which eventually migrates into the cellular phone that we all use 5 to 10 years later. And of course, Wi-Fi began coming into the cell phones around 2002, 2003, when IEEE 802.11b was ratified. And that started this great expansion of data. So while Ada Vera showed the 5G roadmap and the 3GPP all in the last few years and in the coming years, it's really worth noting that it wasn't until very recently, the last few years, that 5G became the first wireless standard in the history of the cell phone industry to go above 6 gigahertz. And fortunately for me, I've gotten to see all these events and know the peoples at the major companies and kind of the leaders in the industry globally. And as one of my colleagues, Seizo Ono-san, who's the CTO of NTT Docomo, likes to say, the even number of cellular standards are generally the ones that are most successful, and the odd number standards are the ones that are kind of the early phase but don't really grab the market. So there's kind of a joke in the wireless industry that the even number of generations are the ones that do great, and the ones that are odd numbered don't always succeed commercially but advance the technology. And if you look at cellular in its history, first generation, or 1G, was analog FM cellular talking only. You could listen to it over a police scanner. In fact, I had a company that did that. And second generation is really when digital happened and when you could start to text. Third generation was supposed to be the promise of the internet coming to the phone, but it really didn't happen until 4G, when YouTube and Lyft and Netflix all could be delivered over your phone. So 5G, being the first move up to millimeter wave, is very exciting. It's pushing the technology. The Apple iPhone 12 has millimeter wave in it. It's a huge challenge for the semiconductors. And I know some of the talking points for this panel discussion will delve into those. So I have some slides that I've prepared for later in this breakout to address those issues. But I thought it'd be worth looking at where 6G is going to be, because 5G is already done from a research standpoint. And now companies like Intel and Qualcomm are commercializing it. And so as a researcher, I like to look at 6G and what that's going to be. So just to take a look at what we're going now above 6 gigahertz for the first time, you saw Ada Vera talk about 71 gigahertz in mobile handsets. Well, the FCC in 2019 opened up spectrum above 100 gigahertz. So 6G, I believe, will be going above 100 gigahertz, which really starts to get into the sub-terahertz and terahertz range. And 2 years ago, the FCC made available 4 new Wi-Fi bands with huge amounts of bandwidth. You can see on the bottom right here, we now have 7 gigahertz bandwidth opened up from 100 up to 250 gigahertz. And I believe that 6G, when it comes to the mobile phone, will allow all these kinds of new ideas. A wireless cognition where human level computation can be sent over the air, where digital twins could be remoted over wireless. Sensing, our cell phone, which right now is a camera and a dictation device and an email device, will become a sensor for air quality, food allergens, explosive detection, gesturing, imaging. It'll be a see-in-the-dark camera. And with these great data rates and bandwidths will come centimeter level positioning. I predict our phone will replace rulers and yardsticks. But one of the things I hope to dispel that a lot of our students and faculty, and maybe some of you believe, is that we're limited somehow when we go above 6 gigahertz, that the channel becomes terrible and it's more attenuative. In fact, that's not so. The whole world of cellular is operated down here around 6 gigahertz or below, but the attenuation due to air is really de minimis, less than a dB going up to 200 or 300 gigahertz. So we're just at the tip of the iceberg of breaking through the sub-terahertz for mobile communications, where so much bandwidth will allow further expansion of the data rate. And this graph shows that rain really is not an issue. Intel and others are working at mobile at 71 gigahertz. You can see that once you go above 70 gigahertz, the rain flattens. So further frequency increases do not really impact coverage in free space, which is really amazing, and most of the wireless industry does not yet understand. And then finally, this will be the last slide. There are a lot of satellites that operate above 100 gigahertz. And these blue areas are the first global Wi-Fi or unlicensed bands opened up by the FCC. England just followed suit a few months ago. But there's all this green spectrum that's available. But there are a lot of satellites that are very sensitive to radio energy coming from Earth. So one of the issues that'll be facing the industry is how to co-locate and how to allocate radio resources for the future mobile industry to expand on all these great applications while protecting those satellites that are very sensitive to interference that comes from the ground. And we've done some of the world's first measurements at NYU, looking at what would happen if mobiles on the ground had good antennas and were transmitting. And with that, I'll stop sharing and turn it over to the next speaker. Thank you, John.
Thank you so much, Ted. Appreciate it. You're muted, Athena.
Sorry. Our next speaker is Ray Chaudhuri. Ray is Distinguished Professor of Electrical and Computer Engineering at Rutgers University and the Director of WinLab, Wireless Information Network Lab at Rutgers University. Ray is WinLab's director, and he's responsible for an internationally recognized industry university research center specializing in wireless technology. He is the principal investigator of several large multi-institutional projects supported by the US National Science Foundation, including the Mobility First Future Internet Architecture Project and the Orbit Open Access Wireless Network Testbed. Dr. Ray Chaudhuri is also active in technology entrepreneurship and is technical advisor to several government organizations and companies. Significant new technology contributions during his career include the satellite data networks, HDTV, high-speed wireless LAN, ATM-based broadband technologies, cognitive radio, content delivery networks, the orbit radio grid testbed, and mobile internet architectures and protocols. Ray, the floor is yours.
Okay, thank you, Athena and John. Thanks for the invitation. Let me just see if I can share my screen. Just give me a second. Okay, do you see the screen?
Yes, yes.
Okay. Thank you for that detailed introduction. I would like to speak a little bit about the potential on the application side generated by these new emerging 5G and edge computing technologies. So I'm going to have a few slides on that. And I want to start by identifying some of the application domains which will be enabled by initially 5G, but eventually it may require something like 6G that Ted was referring to. All these applications involve ultra-high bandwidth and low latency, along with some computing requirements at the edge, which are somewhat distinct from today's traditional 4G applications, where you have a pipe-like network and that takes you into a cloud that could be located at Amazon service site. These are very powerful capabilities for sure, but when we look at some of these applications like augmented reality at scale, we are looking at something fundamentally different. There's an order of magnitude more computational power required, mostly because of machine learning aspects of these applications. In a typical augmented reality application, there is a lot of object recognition and other analytics required at the front end, along with rendering of images that is required after that. All this has to happen with tens of thousands of people in a single microcell or macrocell, which is how cellular operates today, where we have learned how to scale applications like video, but scaling an application like augmented reality is quite challenging if you look at all the numbers involved. Of course, things like GPUs and the NVIDIA technology that we heard about, those are helpful. So a few other applications that involve very low latency is industrial control. You may have heard of Industry 4.0. It's a big area that is emerging, but today's 5G standard kind of aims to address that, but there are performance limitations that have to be overcome. Another area that may be of interest to you, just to show you an example, is that of assisted driving or fully autonomous driving. If you look at these applications, today we are seeing a lot of car crashes take place when people turn on their augmented reality, the self-driving car, and there's kind of been a back to the drawing board kind of approach in the industry where a lot of these services have been withdrawn. And the reason is that machine learning in an isolated way using image processing alone is not sufficient to achieve 99.99% reliability in driving decisions. So one approach that 5G enables is to have an edge network which has a series of base stations along the highway and have edge computing facilities behind that. And this edge computing can then take care of a global mapping and analytics application, which takes input data from hundreds of cars which are on that roadway and are able to compose and analyze them in a way that is useful to the driver or to the self-driving algorithm. That, of course, involves a very rapid amount of computation, and the return has to be within 20 milliseconds or even 10 milliseconds, depending on who you talk to. So these are very challenging network problems. And if you look at the amount of data involved, of course, we do require the gigabit 5G kind of capabilities. But beyond that, we also have to worry about how to get all this computation done through the network in the given amount of time, which is quite small. So the system that we would design to approach this is shown here. So I'm just giving you a system concept for what many of you are familiar with this, I think, which is called mobile edge computing. So in mobile edge computing, you have something like a mobile core network, which you can think of as the 5G infrastructure or the 6G infrastructure. And then you have these edge clusters, which are possibly co-located with base stations. They're spread out, they're heterogeneous, they're low cost, they don't belong to any single big operator. So you are looking at a more of a distributed model where the network is spread out and can gradually stitch together this kind of service as different people post their computing resources. So when you have a typical machine learning application, you could try to run all of it on the client, but typically people will push some of that computation into the edge. And the interesting challenge is how much of parallelism and how much of CPU, GPU processing you need to support this kind of functionality. It leads to a lot of interesting technical challenges which are not solved yet. So I think from the point of view of ECE research, there's a lot of both hardware and software issues in bringing latency down to millisecond. 1 to 10 millisecond is a range that is hard to achieve today. Most machine learning applications actually today consume tens, if not hundreds of milliseconds. And so we really need to improve on that. There's an integration between the network and the computing aspects, which has not been considered too much so far. And so there's a very interesting challenge area of trying to understand how to build distributed edge clouds and how to run distributed parallel processing within these networks, given the challenges of heterogeneity, mobility, resilience, and so on. So it's a very interesting design space which we are focusing on, and we think it will be an interesting one for both ECE and CS communities to work on. I just want to conclude by saying that we are not only doing theoretical work, but we have a project called Cosmos, which is a testbed that NSF funded to look at beyond 5G kind of architectures. And if you're interested, you can look at cosmos-lab.org. There is a multi-layered, fully programmable architecture that allows you to take in a city environment. This is mostly located at Columbia University, who is our partner in this project, and NYU is also a partner. And we have collectively put out some base stations and programmable devices and edge clouds into the infrastructure in Manhattan. So this setup can be used to study some of the scenarios that we discussed before. And just to keep to time, I would just like to briefly show you a demo that we have running of something called a smart intersection. This smart intersection is at the corner of 120th Street and Amsterdam, very close to the engineering building at Columbia University. And with that, we have some cameras which are at the different corners of this intersection and can pick up the traffic and then do different kinds of machine learning based analytics, and then eventually do closed loop feedback. So today I'm not showing any closed loop feedback in the application, but just showing you how different objects like pedestrians or cars are identified and analyzed, and the trajectories and other information can be provided to facilitate augmented reality applications that are running in this space, either for safety or for transportation and so on. And eventually all this plays into the smart city type of space. So just to conclude here, I want to remind you that 5G technology is great, and we look forward to even faster and more bandwidth with 6G, but we also need to pay a lot of attention to latency and computing aspects and focus more on how to truly integrate access network technology with edge computing. Okay, so that's all I have to say now. Looking forward to the discussion. Thank you.
Okay, thank you so much, Ray. We greatly appreciate it. And I'd like to introduce our fourth panelist, Dr. Reynaldo Valenzuela, who's currently the director of the Communication Theory Department at Nokia Bell Labs, and he's also a distinguished technical staff member there. Dr. Valenzuela is currently engaged in propagation measurements and models, MIMO space-time systems, achieving high capacities using transmit and receive antenna arrays, head nets, small cells, and the next generation air interface techniques and architectures. Dr. Valenzuela, he received his Bachelor of Science degree from the University of Chile in Santiago, Chile, and a PhD degree from Imperial College in London. He's a member of the US National Academy of Engineering and also a Bell Labs fellow and an IEEE fellow. So Dr. Valenzuela, the floor is yours.
Hi, can you hear me?
Yes.
Okay, I just realized that I needed to allow permission to use the camera, and to activate that, I would have to shut down the session and start again. So please forgive me, but you'll have to do without the my beautiful face. Man.
Okay. No worries.
Okay,
Yeah.
so let me go to share screen here. Share screen, and I should see an application, PowerPoint. Okay, very good. Can you see my PowerPoint now? Can you all see my PowerPoint?
Oh, we cannot.
We cannot, no.
Hold and, okay, share. Okay, I need to click share.
Yeah,
okay.
we can see now.
There you go.
Okay, so I'm in PowerPoint, and I want to go on the print slideshow. Okay, so you should have a full screen view of my title slide.
Perfect.
And it's a pleasure to be here. Thank you for inviting me. It's a really very distinguished panel and, of course, audience. And I'm going to take a little bit of a different angle. I have been doing propagation for a long time, and I continue to do it. Maybe this is going to bring Ted back to his early days. But I'm a close to the ground kind of guy. So we hear a lot of interesting deliberations and elucubrations and crystal balls predictions. I'm going to try and do, let me get the timer here because I tend to get carried away. So 5 minutes can go flying when you're having fun or when I'm doing the talking. So anyways, a lot of predictions, and we've been around this group before, and I count myself as the skeptic. When the 4G came around, I said, oh, wow, who is going to want to surf the internet on a phone? They're ridiculous. Phones are talking. And I was wrong. I was totally, absolutely wrong. And we're all surfing the internet in our smartphones. Proven wrong. So that's one for me, my skepticism being off base. Well, this time around, I don't want to say told you so, but I just read a very reputable player in the industry come up with a very credible report saying that, at least in Europe, where this vendor is placed, and I am a little parochial, I'm going to be addressing mostly the service provider mobile industry, cell phones, which, you know, it's something like 100 billion per provider in the US, $1 trillion worldwide revenue per year. So it's kind of important. You know, test for size, what is the annual revenue of industry automation or any of a variety of other opportunities out there, and you'll be very surprised. But anyways, at least of today. The report says the return on investment of essentially all the European service providers is negative compared to return on cash on the bank. So they could just take all their money and put it in a bank, and they'll be doing a better business. And there are all sort of reasons, regulatory, they have to pay money because of political, they have to take out some boxes from somebody, forced to put somebody else, whatever. This is far from an exciting, explosive view that we hear from the sort of feudalistic prognosticators. Having said that, I want to give you a good news. This is sort of a 5-minute, very short novel where we start with setting up the tension, and hopefully we're going to release the tension with some great news. 5G was supposed to take advantage tremendously on 28 gigahertz millimeter wave. Well, it turns out that if you look at not the European, whatever they're playing, they're losing money over there, maybe not even America, whatever they're doing in the vast macro. And that's a subject for another talk that may end up more depressing than this one. But if you look at the factory environment, and for a moment, let's do suspension of disbelief, and let's see that one day robots and automation is going to grow to be some fraction of the cellular industry that would be very successful, extremely successful, beyond anybody's dreams. Well, it turns out that factories are not that big. That's number one. If you look at the x-axis, that's distance. If you look at the y-axis, sorry, touching the pad too much. So the y-axis is propagation loss. And the whole game about going to millimeter wave and higher frequencies is that you have spectrum. Now, well, you have spectrum if you have signal. So with TED, we had a friendly disagreement going back to, and I confess, the narrowband of the outdoor macro cellular provider. Is it going to be successful? Is it not going to be successful? And it was all premised upon, do you get enough signal? Well, I think I set up the tension enough already. And so let me release it with telling you the good news. If you are within 100 meters in a factory floor, even if you have the presence of robots and machinery and whatever, you've got plenty of signal. And what I want to impress upon you here is that we have just completed a massive measurement campaign, multiple factories, 4 different factories, and collected data of what I call industrial strength. So this is data that a major vendor can sign hundreds of $1 million contract and guarantee the contract that a certain level of service is going to be achieved 90% of the time, or they need to put up more equipment. So that's the level of statistical confidence you need. The only way to do that, as we did in the old time cellular, is you need to collect a lot of data. And good news for Ted and for me is that if you just go look at the 3GPP books, with all due respect to 3GPP, you're going to be extremely optimistic, because you see the dash blue 3GPP, whatever was closer, is extremely optimistic. If you look at the various factories, you see dash black, dash blue, that's different factories. So it varies tremendously from factory to factory. And if you do, look at the dash red in thick dashes, then that's the entire ensemble. And then you do a 2-parameter fit, and you get only a 7 dB RMS, which, surprise, surprise, is actually not very far from the kind of RMS errors we used to get long time ago when we did HATA over a big area. So we're in good shape. We're in great shape. We have a model. There's plenty of signal if you want to go up to 10 meters. And we can start thinking about what kind of rates. And actually, based on this 2,000 links, more than 100 million individual power samples, we can say, I can give you all the details, but we always talk 90% plus or minus very narrow dBs, not to get caught up with that. Line of sight is near free space, so that's no big deal. You have plenty of sight. But even non-line of sight is only 20 dB below free space. And 20 dB at 100 meters is nothing. You have plenty, you have abundance of signal. But so I'm releasing the tension here. I'm congratulating Ted for being one of the pioneers of bringing us into the spectrum. Indeed, plenty of spectrum, plenty of signal. Everything is cool. And a single base station, which would be actually enough. In a lot of factories, you have hard pressed to find 50 meters on each side of the center. You can deliver 130 megabits per second to 90% of the factory, with a high degree of statistical confidence. And so that's assumed 400 megahertz, reasonable, nothing crazy. The other big news is people think that objects are a big disaster in millimeter waves, because the brain wants to classify, and somehow we were led to believe that millimeter wave is like light. Either you see the flashlight or it's behind the blocker and there is no flashlight. Well, no. Millimeter wave is still very much like fog, car fog lights in fog. It's all over the place. It's scattering, it's diffracting, it's reflecting. And so even if you put a 2-meter square metal plate within 2 meters of the antenna, you only see a 7 dB drop. You already budgeted 20 dB for no line of sight. What's another 7 dB among friends? So forget about blockage. It doesn't happen. And so the signal, what we're saying, and we did, a lot of details, but I'm already past my time here. We did sniffing around with a rotating scanner, angular of direction. And you know what? It comes from surprising directions. So we are not in the business of trying to, after the fact, map it on top of some geometry and say, yes, it's coming from over here. Yeah, that's very nice when you overlay it on something you already know. Predictive power of such is extremely weak. But all we can say is it comes from all sorts of directions, which makes it very nice for avoiding blockage. It has inherent diversity. And so great news, we can do great rates. And I encourage the panel to go and answer the questions. Do we really have a disruptive business in IoT? Or it's just the old-fashioned automated control, process control, owned by the incumbents with little growth ahead? I think I'm being more than abusing you guys' patience. So with that, I finish my.
Great. Thank you
Please.
very much. Greatly appreciate it. So we're going to move now with asking our panelists a couple of questions and on some of these topics. And also, I think, if anybody, once we ask our first questions from the attendees, please raise your hand if they want to ask any follow-up question. All right, I'm trying to make sure that we optimize this process here. But Athena, would you like to go ahead and start with the first question, please?
Yes, so I was planning to ask a question, but they have sort of answered several of these points. But let's summarize. So for 5G, the technologies that were envisioned to be empowering were millimeter wave communications, massive MIMO, and ultra dense networks. Maybe you could comment to what degree these key technologies have delivered on their promise in terms of latency, communication rate, and coverage.
Can I take a quick stab at that?
Sure.
Sure.
Yeah, so I want to sort of make it an exciting panel, so allow me to be the agent provocateur here. There's also another questionnaire that just came out in the US. And if you add the people who don't know what 5G is, don't care what 5G is, or they do have it, but they cannot tell the difference, that's something like 30 to 40% of the users. So maybe it's early, but one, 5G is already being commercial deployment already for, I don't know, 2 years. Two, huge investments by the industry. Three, the street users are telling us very, very weak showing. So whatever it is, the MIMO, massive MIMO, millimeter wave, or a higher bandwidth, it's just not seem to be doing it.
Well, I'll tell you what I've seen. Sprint, which was acquired by T-Mobile last year, was really the only US carrier of the four that was using massive MIMO, and really has shown that to work really, really well in their 2.5 gigahertz spectrum. In fact, Sprint was the only one of the big four wireless carriers in the US that was using time division duplex. All the other three carriers were using frequency division duplex. And with time division duplex, the instantaneous channel is the same on transmit and receive because it's the same RF carrier. And Sprint and its manufacturers, Samsung, Ericsson, Nokia, I believe, have made TDD equipment, which really works well. So massive MIMO is really proving itself. And you can see these funny looking cylindrical base stations. They look like beehives made out of metal starting to pop up all over the country. Those are massive MIMO operating in the mid-band spectrum, the spectrum of 1 to 3 gigahertz. And now the recent auction, which generated about $100 billion, which Verizon and AT&T were the big players in beginning of the year, $100 billion for new spectrum at 3.5 gigahertz. They're also going to likely use some or all of that as time division duplex massive MIMO. So massive MIMO is really delivering, I must say. The other thing, densification, is really happening as well. The FCC made its small cell ruling in 2018 to basically tell all municipalities and states to be friendlier to the wireless industry, because there was a perception by all the wireless companies that there was this kind of hidden tax, a tax of getting access to the right of way that utilities such as gas lines and telephone companies have enjoyed for decades. But the wireless industry, when they wanted to put a tower up or get access to an existing pole, would often face a lot of litigation, years of delay. It was a huge cost. So the FCC created the Small Cell Act in 2018. It's been litigated in lawsuits around the country, but has been backed up, I believe, by the Supreme Court. So it holds, although still local autonomy is given, but it basically has created a legal precedent that now will enable this densification, getting the cell sites smaller and closer to where the people are. Kind of the end game of the cellular industry will be really like Wi-Fi access hotspots, all being closer to wherever people live, work, and recreate. So the Small Cell Act 2018 has really launched a very massive build out of small cells or densification. So I see that happening. The third question you asked about, Athena, millimeter wave, that's been technologically the toughest. And Ada Vera is on the front line of that. She's been doing work on that. She's probably worked on the chipsets and handsets. Intel gave us a riveting talk at our Brooklyn 5G Summit back in 2018 when they had their first generation chips, and Qualcomm did too, and they were showing it really worked. They could put these things in devices. I think now that you see Apple shipping the Apple 12 with millimeter wave and 8-element MIMO antennas, shows you that it works, but it's early days. And as Ronaldo knows so well, working at Nokia and before that Lucent and Bell Labs, it often takes several spins, several chip tape outs before you really hit the sweet spot of price and performance. So millimeter wave is probably the toughest technologically, but it does work. It's working. I know a lot of the carriers and handset makers are having success. I talk to them, and the world is learning about it. That's probably the biggest leap and the newest leap. That's my view anyway.
Can I add a comment?
Please do, yes.
Yeah, okay. So I just wanted to say that that was an optimistic note from Ted. I think all the key technologies for the radio access are beginning to improve and come together. But there is one problem, that none of this is going to work unless the network is improved. And I think I'd like to make the point that traditional 3GPP network standards have evolved quite steadily over the years, and they've gotten more complex, but they still have their circuit switching heritage, which is reflected in concepts like having a tunnel that goes to a central point, which then goes into the IP network. So if you're trying to do a edge cloud, you have to do something different. And that has now been recognized by the 5G community. And there's this concept of standalone mobile core network, which could be used. And then you can introduce some lightweight software-defined solutions to replace some of those standards. So a lot of work needs to be done in terms of making measurements for latency. And what we have found is that almost all the implementations around have excess latency that can be improved but hasn't yet happened. And in order to achieve the promise of 5G, you really have to have a good access network. The mobile core network has to be super low latency and have also very lightweight operation, which can scale to terabits per second. So that whole thing has to happen next. Okay, that's just one point I wanted to make.
I think you want to make a point.
Yeah. So I want to kind of echo part of what you just said and what Ted brought up. There is a difference, and to put it into proper context, the majority of the rolling out that has happened so far has been based on non-standalone. So we know that you're still leveraging the existing 4G core network plus this 5G radio component. You are not really yet seeing the entirety of standalone coming through. It started in 2020, and of course the pandemic has impacted some of that. So that directly affects the performance you can see. Additionally, as Ted mentioned, I think in terms of the spectrum that you're covering, the biggest challenge really does come in terms of supporting FR2. You can support the millimeter wave frequencies, but it comes at significant extra things that you need to have and plan for. And if you want to see the impressive data rates that are promised and all of these things, you need to be able to support all of them. So in terms of just putting it into perspective, once those things keep evolving and coming to fruition, then I think we would get closer to those numbers.
Okay.
Thank you.
Thank you. So I guess I'll close this first set of questions. I think several of you touched in your presentations, but with 5G and maybe beyond, what kind of effects will these technologies have on people's everyday lives, like city planning, human life? Also, I think an important question is, can these technologies will these technologies be easily accessible by all segments of the population, right? There is a cost factor in this. Ted mentioned the iPhone 12. Okay, it's I think clearly, to have everybody be able to have these technologies, the cost has to come down. There's also, areas may be more difficult to put the infrastructure. So, could you please comment on these, topics?
I'll go ahead and start. One of the amazing things about 5G, which never existed before in the cellular industry, is the amount of raw RF bandwidth that's allocated up at these millimeter wave frequencies. By going higher in spectrum, we're able to now have allocated spectrums of several hundred megahertz. And at these frequencies, when you start using MIMO, massive MIMO, directional antennas, which now become very small form factor at these millimeter wave frequencies, you now can get huge data rates that allow 5G for the first time to support multiple users almost as like a fiber optic cable. So I've always believed, for the last almost 10 years, I've been advocating the idea of millimeter wave 5G for backhaul for rural. So the price points on base stations will come down so much that it's conceivable, and carriers are starting to talk about it, but it's always hard to get investments in the rural market. But the idea of using 5G infrastructure as a means of bypassing aging copper in rural markets, because you can get several kilometers line of sight on a telephone pole with a 5G base station and daisy chain along the rural roads, fiber-like quality, or at least much greater data rates than what some people have in rural America. So that's one area where I see 5G being the first wireless standard that could actually democratize internet access in rural areas. I think that's a big area. But it hasn't gotten a lot of attention because rural often has to be subsidized by the FCC for carriers to pay attention to it. But that's one thing that I remain very excited about. And as these rollouts, as they just said, with non-standalone or with standalone, we'll see the data rates and there'll be comfort where those kinds of solutions, I think, will evolve.
Thank you, Ted.
So if I may add a quick comment.
Yes, please go ahead.
So this really begs the question of the much broader issue of not just the digital divide, but equity in our society. And I think we are a little bit too self-centered and arrogant and throw out technology solutions to what is really a much deeper societal problem. I feel too humble to postulate here that this gigabit here and that megahertz there and this millimeter wave over here, we're going to solve societal problems, of which digital connectivity by all means is important, but maybe others equally or more important, like healthcare, food security, etc. So I think that's another photo are more appropriate for that discussion.
No, okay. Thank you.
So I'd like to add to that. So I think 5G has the potential for penetrating into, fairly wide in terms of worldwide penetration. If you look at the experience with Africa and South Asia, penetration of 4G was initially expected to be low because it was believed that smartphones won't be used by people who have limited literacy. But in fact, it turned out to be something like there are more smartphones in India than there are people, and everybody uses it in their own way. And a lot of lower income people also manage to use it. And that goes back to business models and government subsidies and so on. But I think 5G has the potential to bring gigabit, just as Ted said, that in rural and underserved areas, I think there's a potential to bring higher speeds than were possible before with wired solutions. And I think that will be beneficial to the world as a whole. I also feel that new applications are going to come out, and in another 5 years, we won't be looking at the smartphone anymore. In fact, it's kind of silly to pump 1 gigabit per second into a smartphone because it can't even process that in any meaningful way. So I think it would be much better once the application side evolves and we have new applications which can do immersive virtual reality, for example. I think there'll be enormous demand for that, but we are way off from the required performance and cost points for those applications, but it will happen. And I think the next Apple will be the company that figures out what to sell to the mass cellular market.
One of the other points, following on Ray's mention about the higher data rates, I think it's also worth noticing that 5G is the first global cellular standard that also looks at the super slow data rate, super low power application of Internet of Things or sensors, embedded sensors in bridges or vending machines. So IoT is a special part of the 5G new radio standardization that didn't exist before in the other 4 generations. So as well as these super high data rates and ultra low latency that's being built into the standard, also being built into the standard is this very low power, low data rate, heartbeat kind of sensor / IoT application. So that will also be a democratization and will bring 5G and cellular devices into different kind of form factors that Ray's talking about, different devices that use that part of the standard.
So a quick comment to our panel colleagues. This pandemic really opened up the curtain on the vast challenge in front of us. Teachers realized that depending on location, country-wise or within even communities, there could be large fractions of families. They don't have internet connection. They don't have computing. The kids have to drive over to the next hill or to the parking lot of some McDonald's to get internet connection. Yes, cell phones are indispensable, and maybe those people have some form of cell phone. But I think we should be humble and realize that this is a much bigger problem that can be solved with the next G of cellular communication.
Agreed. So let's hold these thoughts. I know there's also a question. Brian wants to ask a question, but Kim, who is making sure we are on time, she's remind me we're a few minutes away from transition to the corporate suites, and then we'll come back and we'll open it up to questions from everybody. But I believe YC Wang would like to do a short presentation, if I'm correct.